This video begins Mazur chapter 12. So the file in the physics 8/files web area is phys8slides12.pdf. The topic is torque. So we have been using for several weeks now Newton's second law, F equals ma, force equals mass times acceleration, or force equals inertia times acceleration. This basically tells you what force does. To find the acceleration of a given object, you take the force applied to it and divide by the inertia. So you could say acceleration is force divided by inertia, although the more conventional way to write it is force equals inertia times acceleration. The direct equivalent of that for rotation is torque equals rotational inertia times rotational acceleration. Just as we see the acceleration as the effect of a force and the mass as a constant of proportionality, we see the rotational acceleration as the effect of a torque, and the rotational inertia is a constant of proportionality. So the rotational acceleration equals the torque divided by the rotational inertia, although again the more conventional way to write it is torque equals rotational inertia times rotational acceleration. Tau equals I alpha. So this is the Greek letter tau. It looks a little bit like the capital T you would see in Old English newspaper print. How do you produce a torque? The way you produce a torque is to apply a force at some lever arm from the rotation axis. So you take a force and you apply it some perpendicular distance, and perpendicular distance we learned in chapter 11 is also called lever arm. And the result of applying a force at some lever arm at some perpendicular distance from a rotation axis is a tendency to produce a rotation about that axis. Tau equals I alpha tells you the effect of a torque. It produces a rotational acceleration inversely proportional to the rotational inertia and directly proportional to the torque. Tau equals R perp times F tells you how a torque is produced. You produce a torque by applying a force at some lever arm with respect to the axis of rotation. This is a meter stick with a hole in it, and we have a little pin serving as a rotation axis sticking through the middle of the meter stick. And if I apply a force directly at the axis of rotation, it has zero lever arm, it has zero tendency to make this rod rotate. If I apply a force out here, which is about a quarter of a meter away, it has a very big tendency to make this meter stick rotate. That's the effect of lever arm. Now if I want to apply two forces with two opposite lever arms, a lever arm to the right and a lever arm to the left, so that they balance one another. Well, these are two copies of the same weight, so I can put them at the same distance on opposite sides of the rotation axis and they will balance. There's not much friction here, so I have to try pretty hard to make it balance exactly. Okay, after some adjustment I made it balance pretty well, so you can see they're basically at the same distance, the same lever arm, the same perpendicular distance out from the axis of rotation, but in opposite directions. So one would tend to make it rotate clockwise, one would tend to make it rotate counterclockwise, and so they balance one another. This is a 200 gram mass. This is a 200 gram mass. Let's try replacing this one with a 500 gram mass. So we have 2.5 times as big a force. So to make them balance, I think I need a lever arm on this side, which is smaller by a factor of 2.5. So to make these two torques balance, I have a 0.25 meter lever arm on this side with a 0.2 kilogram mass, and I have a 0.1 meter lever arm on this side with a 0.5 kilogram mass. So this is 500 grams at 10 centimeters. This is 200 grams at 25 centimeters. And so in the product of this force times this lever arm equals the product of this force times this lever arm, and that balances the torques. If I move this out just a little bit, then we'll create rotation this way. Okay, this is a pretty heavy bicycle wheel, and I have a weight on a string here. It's a 200 gram weight on a string. And if I put the weight just a very small distance, like maybe about a centimeter out from the axle, it has some tendency, but a pretty small tendency, to make the wheel rotate. Now let's take that same weight and put it a much bigger distance out from the axle, and you can see it has a much bigger tendency to make the wheel rotate. It creates a much bigger angular acceleration. So watch this angular acceleration, and then watch this much smaller angular acceleration, and then here in between is an intermediate size angular acceleration, also known as rotational acceleration. Angular acceleration and rotational acceleration are synonyms. We say perpendicular distance because, you see, I could apply the force at a big distance from the axle, but this is a vertical displacement and a vertical force, so I get no torque. But if I apply that same vertical force at a big horizontal displacement from the axle, from the axis of rotation, which is the axle of this bicycle wheel, I get a big torque. So the perpendicular means if you're applying a vertical force, you have to count the horizontal distance between the axis of rotation and the line of action of the force. If you're applying a horizontal force, then you care about the vertical displacement, the vertical distance between the axis of rotation and the line of action of the force. And in general, you want to be careful to pick out the lever arm to be perpendicular to the force, or to use the component of the force which is perpendicular to the way you've drawn the lever arm. So the effect of a force is to produce an acceleration which equals the force divided by the inertia. The effect of a torque is to produce a rotational acceleration which equals the torque divided by the rotational inertia. And the way we get a force to produce a torque is we take that force and we apply it such that the line of action of the force passes some perpendicular distance away from the axis of rotation. So for example, if we wanted to apply two forces to this meter stick, let's suppose this is our meter stick and it is balanced through the middle, and I want to apply F1 at lever arm R_1, and I want to apply F2 at lever arm R_2, and suppose I want to apply these two forces in such a way that the two torques exactly balance one another so that there is zero tendency to rotate this meter stick about this axis, then I want to make sure that F1 times R_1 equals F2 times R_2. And of course I want one of them to tend to rotate clockwise and one of them to tend to rotate counterclockwise. We've been building up for a couple of weeks now this table of correspondence between what we learned about motion in a line or in a plane and what we're now learning about motion in a circle or about rotation. And so we now add the definition of torque. The effect of torque is to produce a rotational acceleration which is proportional to the torque and inversely proportional to the rotational inertia. And the way we produce a torque is to apply a force whose line of action passes some perpendicular distance, some lever arm, from the axis of rotation or hypothetical axis of rotation. This idea of a lever arm actually occurred last week in chapter 11 when we saw how we can convert a linear motion into an equivalent rotational motion. So when we had the momentum of an incoming putty ball, for example, hitting a door at some perpendicular distance, some lever arm from the hinge, from the axis of rotation, that momentum times that lever arm produced an angular momentum. And now we see by complete analogy that a force applied some lever arm away from an axis of rotation produces a torque, which is a tendency to produce a rotational acceleration. I wind a string around a coffee can of radius r. Friction prevents the string from slipping, so the string is somehow wound around the can in a way that the string doesn't slip across the edge, it just unwinds as the can rotates. I apply a tension T to the free end of the string. The free end of the string is tangent to the coffee can so that the radial direction is perpendicular to the force direction. What is the magnitude of the torque exerted by the string on the coffee can? So that's something like this. So here the force exerted by the string is a purely vertical force, and then we want to measure the horizontal distance from the axis of rotation out to the point of application of the force. So we want to figure out where this vertical line of action of the force is perpendicular to this horizontal distance out from the axis of rotation. So we're going to measure horizontal distance, that's r_perp, because it's a vertical force F. And you can see the string is wound in a way that it doesn't slip, so if the can doesn't rotate, then the string doesn't go anywhere. But if we let the can rotate, then if the string goes down by one circumference, then the can goes around by one revolution. Using the numbers given in the problem, the tension in the string is 20 newtons, so that's the force, and the radius of the can is 5 centimeters, or 0.05 meters, so that's the perpendicular distance. So then the torque is r_perp times F, which is 1 newton meter. So the units of torque are newton meters, because it's a force times a lever arm. Force in newtons times lever arm in meters is torque in newton meters. So here's the vertical force and the horizontal lever arm, which tends to create rotation this way. Right now I'm applying two torques to this coffee can. There's a second torque applied by my fingers, which is preventing any rotational acceleration. So if I release the torque applied by my fingers, then there's just the torque applied by the weight on the end of the string. So that's this force times this lever arm. And so you know if we just have that one torque, or if we have, in general, if we have an imbalanced torque applied to the coffee can, then the result will be angular acceleration like this. And then, so suppose the angular acceleration of the can is 2 radians per second squared. You see I wrote 2 per second squared, but that's the same as 2 radians per second squared. When the string exerts a torque of 1 newton meter on the can, what would the angular acceleration of the can be if the string exerted a torque of 2 newton meters instead? So if we double the torque, and if it's the same can, it has the same rotational inertia, angular acceleration is torque divided by rotational inertia. So if we double the torque without changing the rotational inertia, then we must double the angular acceleration. So if the angular acceleration with the 1 newton meter torque was 2 radians per second squared. If we double the torque without changing the rotational inertia, we should double the angular acceleration, so we should get 4 radians per second squared. So I think I like answer D, delta, an angular acceleration of 4 radians per second squared, because it's double the initial angular acceleration, which you should expect by doubling the torque without changing the rotational inertia. This next question says, I apply a force of 5 newtons at a perpendicular distance of 5 centimeters from this rotating wheel, and I observe some angular acceleration alpha. What force would I need to apply to this same wheel at a perpendicular distance of 10 centimeters instead of 5 centimeters to get the same angular acceleration alpha? We have here a wheel that can turn around, and then you see these funny arms spinning in the background. And actually attached to these funny arms, just out of sight, are 2 very big massive blocks, which tend to increase the rotational inertia of this contraption. So it's kind of like a big flywheel, has a pretty big rotational inertia. And then this is a little bit like a bicycle's gear shaft. You have a 5 centimeter radius here, a 10 centimeter radius here, a 15 centimeter radius here. And just as a bicycle's chain can attach to a sprocket at different radii for different gears, we can apply a force by using a string wrapped around the 5 centimeter wheel, or wrapped around the 10 centimeter wheel, or wrapped around the 15 centimeter wheel, and it's causing the same mechanism to turn. So if we apply a given force, we can apply the force here and say what's that torque. We can apply the force here and say what's that torque. We can apply the force here and say what's that torque. Here's my half kilogram mass. So I'm going to apply 5 newtons at a distance of 5 centimeters, a displacement of 5 centimeters. And notice this force is downward and the displacement is horizontal. So the sine theta factor between the displacement and the force is 1. So it's just 5 centimeters times the tension in this string is the torque. So 5 centimeters, it's actually 0.05 meters, right? So in Newton meters, 0.05 meters times the tension in this string is the torque in Newton meters that I'm applying with this mass. If this mass is not accelerating downward, if it's just hanging here, then the tension in this string equals mg, which is 5 newtons. If I let go of this and it starts accelerating, then technically the tension in this string is no longer mg, it's mg minus ma, where a is the downward acceleration. You have to bear that in mind, but to keep things simple, let's pretend it's mg rather than mg minus ma. And that actually is not a bad approximation because you're going to see that this thing doesn't accelerate downward anywhere near g. So let's just say it's mg, even though we know it's mg minus ma. Now capture in your mind's eye how big is the angular acceleration. So that means like how fast it goes around and faster and faster and faster. And how often it goes around is the angular velocity. The rate of change of how often it goes around is the angular acceleration. So you're going to see it go around and around and around faster and faster. That's the angular acceleration due to this torque. Okay, let's watch that. Okay. Now, I want to try to get that same angular acceleration, and it's the same flywheel, but I want to get that same angular acceleration by applying a force at 10 centimeters instead of applying a force at 5 centimeters. This was a 5 Newton force. So how big a force do I have to apply at 10 centimeters to get the same torque and therefore to get the same angular acceleration? 0.05 meters times 5 newtons is the same as 0.10 meters times 2.5 newtons. So instead of 5 newtons, I want 2.5 newtons. And the way I get 2.5 newtons is instead of using a 500 gram, half kilogram block, I'll use a quarter kilogram block, a 250 gram block. We now have a 2.5 Newton force at a lever arm of 0.1 meter. So we should get the same angular acceleration we got last time. Let's see if it looks the same. For comparison, well, let's see what happens if we apply that 2.5 Newton force at the original 0.05 meter displacement. Now, do you expect a bigger or a smaller angular acceleration? This is half the torque, but the same rotational inertia. So I think we'll see half the angular acceleration we saw before. Let's see what that looks like. One more data point. Let's put the 5 Newton force at the radius at the displacement of 10 centimeters, 0.1 meter. So now we have at a lever arm of 0.1 meters, we have a force of 5 newtons. So this should be twice as large a torque as we had when we had the 2.5 Newton force at 0.1 meters. So this should be the biggest angular acceleration we've seen yet. Let's see. Okay. Since we haven't changed the rotational inertia, to get the same angular acceleration, we would have to apply the same torque. I applied a force F1, which was 5 newtons at a perpendicular distance. Our perp1 was 5 centimeters from the center of the wheel. So if I want to get the same torque at a distance of 10 centimeters instead of 5 centimeters, so I've doubled the lever arm, so I want to cut the force in half to get the same torque. So you can see going from the original torque to the new torque, I have doubled the lever arm. So if I have twice the lever arm, I want half the force to get the same torque. So if I initially applied 5 newtons at 5 centimeters. Instead, I should apply 2.5 newtons at 10 centimeters to get that same torque. And then for the given rotational inertia, that should be the same angular acceleration. So the original torque that I applied was 5 newtons at a lever arm of 0.05 meters. So that gave me 0.25 newton meters. To get the same torque and therefore the same angular acceleration using a lever arm of 0.1 meters, I have to apply a force of 2.5 newtons. So if I double the lever arm, I cut the force in half to get the same torque, and that same torque will give me the same angular acceleration, assuming that it is the same rotational inertia. Suppose I use the tension T in a string to apply a given torque, which is r perp times T, to this wheel, and the wheel then experiences a given angular acceleration alpha, also known as a rotational acceleration alpha. Now I increase the rotational inertia of the wheel. How am I going to do that? Well, this particular wheel has some adjustable masses, and they're positioned symmetrically, and so I can put them both in close to the axis, or I can put them both far away from the axis, and by doing that, that mr squared factor increases or decreases the rotational inertia of this big wheel. Somehow I'm moving the mass closer to the axis to reduce the rotational inertia, or I'm moving the mass farther away from the axis to increase the rotational inertia. So I increase the rotational inertia I of the wheel and then apply the same torque. The new angular acceleration will be, well, angular acceleration is torque divided by rotational inertia. So if you keep the same torque, but you make that rotational inertia bigger, then you expect a smaller angular acceleration. So I like answer C, Charlie. The new angular acceleration will be smaller than the original angular acceleration because we applied the same torque to a system that had a bigger rotational inertia. So that's a smaller rotational acceleration. So this is the angular acceleration we get with a 5 Newton force at a displacement of 0.1 meter. Now, let's apply that same force at that same displacement, so that's the same torque, but let's find a way to substantially increase the rotational inertia of this device. Same force, same displacement, therefore same torque, but we have dramatically increased the rotational inertia of the red wheel by putting these big masses out farther from the center. Let's see what the angular acceleration is now. Oh, that's really pretty slow. Okay, so this is illustrating that torque equals the product of rotational inertia times angular acceleration. So just as acceleration is force divided by mass, we have angular acceleration as torque divided by rotational inertia. Here's an example reading question I've used for a while. I want to tighten a bolt to a torque of 1 Newton meter, but I don't have a torque wrench. A torque wrench is a wrench which applies a known torque. I do have an ordinary wrench, a ruler, and a 1 kilogram mass tied to a string. How can I apply the correct torque to the bolt? Well, let's suppose I orient the wrench horizontally and I hang the mass at a distance of 0.1 meter from the axis of the bolt. Let's try that. So if I put this mass a distance of 0.1 meter from the axis of the bolt, I guess I drew a nut here, but R perpendicular is 0.1 meter, and then if it's a 1 kilogram mass, then that's a force of about 10 newtons, let's say 9.8 newtons. We can round it to 10. That's 10 newtons times 0.1 meter. That seems like a torque of 1 Newton meter. So I think this should do the job, although I'm neglecting the fact that the weight of the wrench itself is applying an additional torque. So I suppose to do this, I would have to do it with a wrench which is much, much less massive than this weight that I'm hanging here. Or somehow I would have to correct for the torque due to the weight of the wrench. And actually that would be the center of mass of the wrench. So I say how far out from this axis is the center of mass of the wrench, and then I can multiply that lever arm by the weight of the wrench, and that would be an additional torque in the same direction. If we take the center of mass of the wrench, then there's an additional torque, which is the mass of the wrench times G is the force, and then there's the distance from the bolt axle to the center of mass of the wrench. So I suppose in the original question statement, I was assuming that this additional torque due to the weight of the wrench times the lever arm from the center of the bolt to the center of mass of the wrench was negligible, but it may not be. So if it is, then I suppose you would move the point of application of this additional mass in so that the sum of those two torques is a desired torque. But let's suppose we do this with a wrench that on its own has negligible mass. So then we do just want to apply our 10 Newton, 1 kilogram mass times G is about 10 Newtons. We want to apply our 10 Newton force, a lever arm of 10 centimeters, 0.1 meter from the bolt axle to give us a 1 Newton meter torque going this way. So I like answer A. If you got answer B, you might have forgotten to include the little g to convert the mass into the weight. And of course you want the force, which is mg times the lever arm. The torque is the force times the lever arm. The force in this case is the weight, not the mass, but the weight. So the weight is the mass times little g. And then we take that weight and multiply it by the lever arm, and that gives us the torque. Suppose now that the same wrench is at a 45-degree angle with respect to the horizontal, but we still have this 1 kilogram mass, and it is still a distance of 10 centimeters, 0.1 meter, from the bolt axis. So it's suspended at a distance 0.1 meter along the wrench. Will it still exert a torque of 1 Newton meter on the bolt? Or as I've drawn it here, a nut instead of a bolt. Well, you could say, gee, the force of gravity hasn't changed and the distance hasn't changed. Maybe it's the same torque. Or you could say, well, no, I think the torque is now larger. Maybe it's larger by a factor of the square root of 2. Or you could say, gee, maybe the torque is now smaller. Let's say maybe it's smaller by a factor of the square root of 2. Well, I think it's the same force, but the perpendicular distance, how is it the same or has it changed? I think instead of wanting to use the whole distance, now we want to use just the perpendicular part of the distance, the part of the distance which is perpendicular to the line of action of this force. Since this is what's a string hanging, but it's basically hanging vertically, so this is a vertical force, so we want the horizontal distance to go with the vertical force. So we want to pick out just the horizontal part of this distance, and that horizontal part of this distance goes with this vertical force. So I think we're going to get a smaller torque. Let's see how much smaller. So in this case, my distance d was 0.1 meter, and my force mg, the tension in the string, which in this case is just mg, is 10 newtons. But I don't want the whole distance. R perp here, the perpendicular distance from the axis of rotation to the line of action of the force, is just the horizontal part of this displacement. It's not the entire displacement. Since I have a vertical force, I want the horizontal displacement. So I can pick out the horizontal component of this displacement by drawing a triangle here, and I say, aha, I must want this distance times the cosine of this angle with respect to the horizontal. So that's the distance times the cosine of 45 degrees. The cosine of 45 degrees is 1 over the square root of 2, which is about 0.71. So it seems like R perpendicular is about 0.71 times this 0.1 meter distance. So my torque will be R perpendicular times the force. R perpendicular is just d over root 2, which is 0.071 meter, right? So I take 0.1 meter and I multiply it by this factor of 0.71, and that gives me 0.071 meters. The force is still 10 newtons, so 0.071 meters times 10 newtons is 0.71 Newton meters. So I think I like this, 0.71 Newton meters. One thing to bear in mind about this diagram that's pretty tricky is we wanted to pick out the horizontal component of this force, and this theta was measured with respect to horizontal, so we used the cosine of this angle. But bear in mind that the cosine of this angle is the sine of this angle. So this angle that we drew as theta is the angle between the actual displacement vector and the horizontal, because we knew we wanted to pick out the horizontal part. But we could have asked, what is the angle between the line of action of the force and the displacement? So that angle between the line of action of the force and the displacement vector is actually this angle that we didn't label. I don't really want to label it right now because we'd have to choose a symbol to label it with, and I'm not sure what symbol to choose. But bear in mind that because we have a right triangle here, the cosine of this angle down here equals the sine of this angle up here. And this angle up here is actually the angle between the force vector and the displacement vector. So it's actually more common to consider the angle between the force vector and the displacement vector. Although in this particular case of the wrench problem, we knew we wanted to pick out the horizontal part of the displacement because the force is vertical. We know that a vertical force will go with a horizontal displacement. So we drew the angle here so that it would be easy to pick out the horizontal component. In general, if you have a force and a displacement at some arbitrary orientation, then you want to ask yourself, what is the angle between the force and that displacement? So suppose we have the more general case where the vector from the axis of rotation to the point of application of the force is not perpendicular to the force. So here I've drawn the line of action of the force in blue, and I've drawn, and here up at this intersection point is the point of application of the force, and then here's my rotation axis, and I've drawn this vector r from the rotation axis to the point of application of the force. So if we want to get the magnitude of the torque due to applying this force at some non-zero lever arm here, we have several ways to do it. The first way, which we've been using, is to pick out the perpendicular component of this displacement r. So since it's a vertical force, we want to pick out the horizontal part of r. Another thing we could do is, since we have this displacement vector in this direction, we could pick out the perpendicular component of the force. Now in this case, since the force is drawn as a vertical line, it's easy to pick out the horizontal part of the displacement. Sometimes the displacement is horizontal and you have a diagonal force, so then it's pretty easy to pick out the vertical part of the force. Or sometimes you have a purely vertical displacement and you have a diagonal force, so then it's easy to pick out the horizontal part of the force. So if either the force or the displacement is naturally along some easy to use axis, then often it's easier just to pick out the perpendicular component of the other one. So if you happen to have a nicely vertical force, you can just pick out the horizontal displacement. If you happen to have a nicely horizontal displacement, you could just pick out the vertical part of the force. In general, there's some angle theta between the displacement vector r and the force F. If these were perpendicular to one another, then that angle theta would be 90 degrees. So if the angle theta is 90 degrees, the sine of 90 degrees is 1. So ideally, you would like this displacement vector and this force vector to be perpendicular to each other, and then multiplying by the sine of this angle is just multiplying by 1. So we can say the torque, the magnitude of the torque, is the perpendicular part of the displacement times the force. In this case, the perpendicular part of the displacement would be picking out this component like that, or we could pick out the perpendicular part of the force like that, or we can take the entire displacement magnitude times the entire force magnitude times the sine of the angle between the displacement and the force. And again, we use the sine to pick out the perpendicular part. Remember, when we did the dot product, we were using the cosine to pick out the parallel part. In this case, we're using the sine to pick out the perpendicular part, and that's because, in exact analogy with our expression involving the cross product for angular momentum, there's actually an expression for torque, and we actually later we'll see torque as a vector. So torque as a vector is the displacement vector cross product with the force vector. And if we take the magnitude of the torque, then it's the magnitude of this cross product. And the magnitude of this cross product is the magnitude of this vector times the magnitude of this vector times the sine of the angle between them. So 4 ways to get the magnitude of the torque. We can take the perpendicular component of the distance times the entire magnitude of the force. We can take the entire distance times the perpendicular component of the force. We can take the entire distance times the entire force times the sine of the angle between the displacement and the force. Or equivalently, we can take the magnitude of the vector product r cross f, which is also called the cross product. So there's this thing called the vector product or the cross product. You calculate it using the right hand rule. My right hand looks like a left hand with the light board flipped. So that's 4 different ways to calculate the magnitude of the torque. You can use whichever one is most convenient for a given situation. To tighten a bolt, I apply a force of the same magnitude F at several different positions and angles. In which case do I get the largest torque? It seems like in case F, I am using the entire distance and the force is perpendicular. So the sine theta factor is 1. So this is the entire length of the wrench times the force, and the sine of 90 degrees is 1 since they're perpendicular. So I think I get the entire F times the entire distance in this case. Actually, this seems to be clearly biggest because there's no place else that I'm applying the force at the entire length of the wrench. So here I'm using this, it's perpendicular, but it's a smaller distance. Here it's perpendicular, but it's an even smaller yet distance. And it seems like C and D are the same magnitude, but in opposite senses. So one is clockwise and one is counterclockwise. And if we look at A and B, in both cases the force is applied at an angle. So if we have a horizontal displacement, see here's a case where we have a horizontal displacement, so it would be convenient to pick out just the vertical vertical part of the force. So to get the torque, we have the horizontal displacement times the vertical component of the force. Here we have the horizontal displacement times the vertical component of the force. So it seems like B would actually be a smaller torque than D because the distance is the same, but we only get a portion of the force for B, whereas for D we get the entire force. I think C and D would be the same magnitude but opposite directions. And then E is a small displacement but the entire force. A is that same displacement as E, but it's even a smaller, effectively a smaller force because we only get the vertical portion of the force. In any case, this question is saying which torque is largest. So I think it's clear that situation F, Foxtrot here, situation F has the largest torque because it's the entire force, because it's perpendicular, and it's the entire length of the wrench. So I like F for the largest torque. Now in this case, which torque is smallest? It seems like the smallest displacement from the axis of rotation is like a tie between A, alpha, and E, echo. However, here the force is perpendicular to the displacement. Here the force is at a funny diagonal angle. So we actually not only have a small displacement for A, but we also have to pick out only the vertical component of this force. So I think A, alpha, is the smallest torque because not only is it a small distance from the axis of rotation to the point of application of the force, but because the force is not perpendicular to the displacement, we get only the perpendicular portion of the force, which is smaller than the entire force. I want to apply to this meter stick two torques of the same magnitude in opposite sense. In other words, one clockwise, one counterclockwise, so that the stick has zero rotational acceleration. I apply one force of 5 newtons at a lever arm of a half meter. So here's a half meter, this is a meter stick, here's a half meter, and this is half a kilogram. So using G is about 10, that's 5 newtons. And you can see the hole in the stick isn't quite all the way at the end because you can't put a hole all the way at the end, but it's pretty close to half a meter. I want to apply an opposing force at a lever arm of 0.2 meters. So there's 0, 0.1, 0.2, so that the second torque balances the first torque. How large must the second force be? Well, I think you want horizontal distance times vertical force equals horizontal distance times vertical force. So if this is 5 newtons at a half meter, then this is 2/5 the distance, so we must have to have 5 halves the force, so that's 5 times 5 over 2 is 25 over 2 is 12.5. So I think we need 12.5 newtons. In fact, this is 1.2, 1.25 kilograms. So I put 1.25 kilograms over here, I put a half kilogram over here, and they balance. And to convince you that I had to make them balance, I could, well, if I remove this, you see they don't balance and it starts to tip over. To repeat, we put a 5 Newton force perpendicular at a perpendicular distance of a half meter, and that gave us a 2.5 Newton meter torque. In the other direction, we put a 12.5 Newton force at a perpendicular distance of 0.2 meters. That gave us a 2.5 Newton meter torque. So these two torques about this axis of rotation balance one another because one tends to go this way, one tends to go this way. They have the same magnitude in opposite sense, so the meter stick was balanced. So I want to apply to this meter stick two torques of the same magnitude in opposite sense so that the meter stick has zero rotational acceleration. I apply one force of 10 newtons at a lever arm of a half meter. So this is a vertical force of 10 newtons at a horizontal lever arm of a half meter. I tie a second string on the opposite end, a half meter from the pivot point. The pivot point is in the middle here, so this is a half meter horizontally, this is a half meter horizontally. But now the second force is applied at an angle which is 45 degrees away from the vertical. How large must this second force be? Well, one way to analyze this would have been to say, let's take the line of action of the force and extend it until it's perpendicular, and then figure out the smaller r perp. So we could have extended the line of action up to here and said, oh, this is r perpendicular. But that turns out to be inconvenient for this problem. Instead, we want to say, let's just pick out the vertical part of this force. And the vertical part of this force, in this case, since it's a 45-degree angle, is just this force divided by the square root of 2, which is the force divided by 1.414. So we only get a fraction 1 over 1.414 of the force. So in order to balance, it's the same horizontal distance, but this is a perfectly vertical force. This force is at a funny angle. So we only get 1 over root 2 of the force that we apply. So in order to get the same torque, we have to apply a force which is bigger by a square root of 2. So we need to apply a force which is bigger than the left-hand force, bigger by a square root of 2. So we need to apply a 14.1 Newton force instead of a 10 Newton force, since we only pick out the vertical part. So if the magnitude of this force is 14.1 newtons, then the vertical component of it will be 10 newtons, and these torques will balance one another. So I like answer D, delta, for this question. We have 10 newtons downward at 0.25 meters, so that's a clockwise sense. And then we'll have an unknown force upward, so that'll be a counterclockwise sense with respect to this pivot. Unknown force at 0.5 meters. So if this is 10 newtons, how big will this unknown force be so that the torques balance? Let's see. Okay, 5 newtons. So 5 newtons at 0.5 meters balances 10 newtons at 0.25 meters. So this will still be 10 newtons downward at 0.25 meters. Now what if we apply this force at a 45-degree angle? How big does the force then have to be? If I'm holding everything just right, then you should get about 7 newtons. You want the upward component of this force then to be 5 newtons. And so the force goes this way, the upward component is this force times the sine of 45 degrees. If this rod doesn't accelerate rotationally about this pivot, so here is a pivot, and then we go out, and this is the point of application of the force, and I hang a 1 kilogram mass here. So 1 kilogram kilogram of M gives me mg equals 9.8 newtons. Let's call that 10 newtons. So we have 10 newtons down. What force do I have to apply up to balance it? So this 10 newtons down gives me a clockwise torque. So I want a counterclockwise torque upward of the same magnitude. It's actually at the exact same lever arm, so I guess it just has to be 10 newtons up. So I have 10 newtons up, 10 newtons down applied at the same lever arm. Those two forces, those two torques balance. So D, delta, I only need 10 newtons here because I have 10 newtons downward, that gives me a clockwise torque. Then I have 10 newtons upward, that gives me a counterclockwise torque, and they balance one another. So I have my pivot, and half a meter out from my pivot, I have a 1 kilogram mass. That's a downward force of 10 newtons. The second force I'm going to apply is at the same distance. This tends to accelerate clockwise. This will tend to accelerate counterclockwise. So how big will this force be to make the torques balance? Did you say 10 newtons? Good. Okay, now here's the pivot way on the left, and halfway across the ruler I have an unknown force which is upward. Then all the way across I have a 10 newton force which is downward. So 1 kilogram times little g is 9.8 newtons. We'll call that 10 newtons. So we have 10 newtons downward. Now a downward force would tend to be a clockwise rotation, and an upward force here would tend to be a counterclockwise rotation if the tendency is to rotate about here. So here we're rotating clockwise about the pivot with this downward force, and this upward force is tending to produce a counterclockwise or anti-clockwise rotation about the pivot. So the typical convention that we use is anti-clockwise minus clockwise. So the counterclockwise torques we do with a plus sign, the clockwise torques we do with a minus sign. You could use the opposite convention if you want. It's just nice to have a convention. So we see we draw this little anti-clockwise arrow, kind of a curved arrow, that's saying our convention is, our sign convention is that we're going to be counterclockwise about this pivot. So this is an unknown force up F at a lever arm of L over 2, and then here is a 10 newton force at a lever arm of L, and this has a minus sign because it is clockwise, this has a plus sign because it is counterclockwise about this pivot. You see, if we pivot about here, this force would tend to make a anti-clockwise rotation, this force would tend to make a clockwise rotation. So in order for these two things to sum to 0 so that the rod doesn't accelerate, then we need this unknown force to be 20 newtons. So I think I like answer F, Foxtrot here, 20 newtons. So we have 10 newtons at 0.5 meters, we have an unknown number of newtons at 0.25 meters. How many newtons will this be? How about 20? Okay, now we basically reverse the position, so we want to balance the two torques. So here's one clockwise torque about this pivot, and here's one anti-clockwise torque about this pivot. So we're using the convention that anti-clockwise is positive, so we'll do positive minus negative. So this is a lever arm of L times an unknown force F upward. This is a lever arm L over 2 times a known downward force 10 newtons. So we'll do positive minus negative, anti-clockwise minus clockwise. Lever arm L times force F minus lever arm L over 2 force 10 newtons. So F must be 5 newtons. So I think I like answer B, bravo here, that the force must be 5 newtons. So 5 newtons times L is the same magnitude as 10 newtons times L over 2. This one tends to rotate counterclockwise, this one tends to rotate clockwise. So they have opposite sense. Okay, now we're again applying two forces. They result in two torques. We want the two torques to balance so that the rod does not accelerate. Here's the pivot point. Our convention again will be counterclockwise is positive. Here's a lever arm of L over 2. L over 2 horizontal lever arm, 10 newton vertical force, that's clockwise. Now we have a lever arm of L, but this force is applied at a 45-degree angle, so we only get to pick out the vertical part. So if this is magnitude F, the vertical part is F divided by square root of 2. And this would tend to rotate counterclockwise, that's our positive sense. So we pick out the vertical part of F, that's F over root 2, and then the distance is L. That's positive because it's counterclockwise. Then the clockwise part is 10 newtons, L over 2, and those should sum to 0. So I think this force that we apply here has to have magnitude 10 newtons divided by root 2, which is 7.1 newtons. See, the vertical part has to be 5 newtons. Since this has twice the lever arm, this is 10 newtons down, so 5 newtons up at twice the lever arm would balance, but 5 newtons up is the same as 7.1 newtons at a 45-degree angle. So the force that we need to apply is 10 newtons times root 2 over 2 is 7.1 newtons, because this anti-clockwise positive torque is F over root 2, that's picking out the vertical part, is F over root 2, times L, and then this clockwise part is 10 newtons at a lever arm of only L over 2. So those two terms balance one another. That gives us the magnitude of F, which we apply diagonally, is 7.1 newtons. That looks like roughly 45 degrees. So if I'm holding everything just right, then you should get about 7 newtons. Okay, so we're again pivoting about this left end of the meter stick, and we have a downward force of 10 newtons applied at a lever arm of L over 2. So this is horizontal distance L over 2, vertical force 10 newtons, clockwise sense. We want to balance it with a counterclockwise torque. So here we are applying the force at the full length of the meter stick, that's L, but now we're making a 30-degree angle with respect to the horizontal. So we want to pick out just the vertical part of this force. So this is F perp. See, the part of the force which is perpendicular to the displacement, and that would seem to be be f sine 30 degrees. So the displacement is horizontal, so we want just the vertical part of the force. This is f. The vertical part of f is f sine 30 degrees. So we'll do anti-clockwise minus clockwise. So this is f sine 30 degrees times L minus 10 newtons times L over 2. Horizontal displacement times vertical force, horizontal displacement times vertical force. Anti-clockwise is positive, clockwise is negative. Sine of 30 degrees is a half. This is f times a half times L minus 10 newtons times L over 2. So that works out if the force is 10 newtons. So I think I like D, delta. The force is 10 newtons. So it turns out that angular momentum is a vector, and it turns out that torque is a vector. And you might wonder, how do you associate a vector in space with something which is rotating or tending to cause rotation? Well, because we live in three-dimensional space, when something rotates, rotation really takes place in a plane. So there's some plane in which everything is rotating here. If I tend to cause something to rotate, all of that rotation happens in a plane. But it's convenient to use the vector perpendicular to that plane of the rotation to represent the rotation itself. And that works because we're in three-dimensional space. So really, rotation is represented by a plane, because when you make something rotate, you're rotating things within a plane. But in three-dimensional space, we have the convenient option of using the vector perpendicular to that plane to represent the plane of rotation. Now that still leaves us a sign ambiguity. So you can say that the motion of the hands of a clock clockwise can be represented by an axle which is perpendicular to the face of the clock. But then you say, well, is the motion of the clock the arrow that points into the board, or is it the arrow that points out of the board? And the convention is that the motion of a clock is the arrow that points into the face of the clock. Now this is actually my right hand, although I mirror the video for the light board, so it looks to you as if it's my left hand. But using my right hand, if I wrap my fingers of my right hand around in such a way that my fingers are pointing the way the clock hand moves, then my thumb points into the plane of the board. So see if you can do that with your right hand. I know it's a little confusing because I mirror the video, but if you twist your fingers around so that your fingertips are pointing the way the hands of a clock move, then you'll find that your right thumb points into the plane of the clock. So the vector that we use to represent clockwise motion points into the face of the clock. If we have a vector, let's say this is R and this is F, and let's say this is R and this is F, then we take R cross F with the right hand. So you start out with the fingers of your right hand moving along the R vector, the displacement vector, and then you curl the fingers of your right hand so that they subsequently point in the direction that the force is pointing. And then you ask, which way is your thumb pointing after you're able to do that? And in this case, my thumb is pointing out of the plane of the board. So I take a vector to the right, cross product with a vector up, and it gives me something that points out of the plane of the board. By contrast, if I take a vector that points to the right and I do the cross product with something that points down, then my thumb points into the plane of the board. This is using my right hand, although it looks like a left hand to you. So this is R cross F, and it points into the plane of the board. So the convention is, now you know that this would be a clockwise torque, and you know that this would be a counterclockwise torque. So a counterclockwise torque by convention points out of the plane of the board. A clockwise torque by convention points into the plane of the board. That's the so-called right hand rule. Almost every screw or bolt that you pick up, except for certain screws that are made backwards for safety reasons, almost every screw that you pick up will have right-handed threads. So that means if you turn in a clockwise way, the bolt will move away from you. So when you tighten a nut or a bolt by turning clockwise, that bolt tends to move away from you. And if you move counterclockwise, then the bolt will tend to move toward you. That is a right-hand threaded bolt or screw. It's possible to manufacture bolts or screws the other way, but the convention is that 99.9% of bolts and screws have right-handed threads, meaning that if you turn in the direction that your fingers of your right hand curl, then the screw or bolt will move in the direction of your right thumb. Try that out and check it out the next time you have a bolt or a screw in your hand. There are a few examples of places where screws or bolts are threaded the other way, and sometimes it has to do with safety mechanisms on things that rotate, like rotating pieces of machinery. Sometimes there's a desire to make things deliberately incompatible so you don't thread incompatible things to each other, so one of them will be made left-handed threaded so that you can't accidentally connect it to something which is maybe more common but incompatible. If you look at the face of a clock whose hands are moving clockwise, do the rotational velocity vectors of the clock's hands point toward you or toward the clock? Well, they point toward the clock. I'm looking at the clock, they point toward the clock. So the clockwise direction is into the plane of the board by convention. So we're actually reaching a really interesting and important and fun part of the course. We're going to see, now that we have, remember at the beginning of the course, Professor Farley told us that in order to look at structures, we need first to have three things under our belt. We need to understand forces, vectors, and torque. So we did forces when we got to chapter 7 of the textbook. We did vectors when we finally got to motion in a plane, and we learned how to decompose forces on an inclined plane, for example, into their components. And now finally we're getting to torques, and we're just getting our feet wet with torques, but pretty soon we'll understand torques and how to use them. So torques are important in architecture because they allow us to determine the conditions for a structure to stay put. So for an object like a structure or a part of a structure to stay put, it must have zero acceleration and it must have zero rotational acceleration. So you don't want a piece of a building to accelerate, and you also don't want a piece of a building to accelerate rotationally. So the vector sum of all forces on a structure or a part of a structure must add to zero, and the sum of all torques about any axis using the appropriate sign convention must also be zero. So then you keep the acceleration is zero for every part of a structure, and you keep the rotational acceleration zero for every part of a structure. If these conditions are met, the object is in equilibrium. That means there are no unbalanced forces and there are no unbalanced torque. So writing the conditions for equilibrium is a fundamental part of analyzing structures. So we will spend a lot of time doing that. So that will be the next thing that we do when we pick up and move ahead using our understanding so far of forces and torques and vectors. So let's resume our discussion of Mazur's chapter 12 on slide 23 of phys08 ch12.pdf. And one major topic we're going to cover as one of our most fun applications of torque is static equilibrium. Now in real life, things live in a three-dimensional world, and we have three coordinates, x, y, and z, but normally we draw things on two-dimensional sheets of paper. So we will focus for now on static equilibrium in two dimensions. So then we have two coordinates, x and y, and the conditions for equilibrium, meaning that the object does not accelerate and it does not rotationally accelerate, are that all of the forces in the x-coordinate add to zero. You have to assign the proper sign to each force so that they can balance each other with canceling signs. All of the forces in y sum to zero, and all of the torques sum to zero. You have to choose a sign convention. Our usual sign convention is counterclockwise is positive, clockwise is negative, and you add up torques about some chosen axis. Nothing is really rotating in these problems, so the choice of axis requires a little bit of ingenuity, and we will see from examples often the best choice of axis is such that the line of action of a force whose value you don't care about passes through the chosen axis, so that you get equations as a result that simply do not depend upon the force that you don't care about. Here's a question that brings us back to the hands-on exercise we did in the very first day of class. If you have a beam supported on two columns asymmetrically like this, then which column supports more of the beam's weight? And in a configuration like this, if you tried it on the first day of class, you probably found that this right-hand column supported more of the weight and this left-hand column supported less of the weight. And the key to understanding that was that this column is farther away from the center of mass and this column is closer to the center of mass. And I suggested that you use the analogy of a seesaw and imagine two kids on a seesaw at different distances and imagining how the two kids' weights could differ in order to get them to balance the seesaw at these two locations. Now that we know about torque, we can see directly why the seesaw metaphor makes perfect sense. So after annotating our diagram, let's analyze this beam configuration, and then we can go back and look at the demonstration from the first day of class using two scales. So I annotated this diagram. So here is the center of mass of the beam, and I have the gravitational force pointing downward, and then here are the two contact forces on the left by column 1, on the right by column 2, and then I indicated the relevant dimensions up here, which are the horizontal distances from the center of mass to the point of contact of column 2 and of column 1. It's usually easier to redraw a diagram that just picks out the object of interest. In this case, we're interested in forces and torques acting on the beam, so we just draw the beam and we label it beam. This diagram will be called an extended free body diagram, EFBD. You want to include on the extended free body diagram usually an indication of the center of mass of the object, all of the forces acting on the object, and in this case you actually want to be sure to indicate the correct line of action of each force. So that shows the point of application of the force and the direction of the force. In the case of the gravitational force, we treat it as if its effect were entirely concentrated at the center of mass of the beam. We draw an arrow passing through the point of application of the force, which is the center of mass or center of gravity of the beam, and pointing downward. We label it the gravitational force by Earth on the beam, and then we know its magnitude is mg. Here we draw the contact force by column 1 on the beam, and we're just calling that F1 for short, and it's convenient in this case to make the tip of the arrow indicate the point of contact. Over here we have the contact force exerted by column 2 on the beam, so it points upward. This points upward. They're contact forces, normal forces, and we label this F2 for short, and then we'll see in a moment why we want to indicate this distance. Since these are vertical forces, we'll be interested in the horizontal distance between the center of mass and F2 and between the center of mass and the line of action of F1. How do we say that the forces sum to zero in the y coordinate? I like to write up minus down. It often helps to write your axis convention on the diagram somewhere. Up minus down would be F1 plus F2 minus mg equals 0. That makes sense. The two upward forces exerted by the two columns on the beam must sum to the weight of the beam. Now actually, 0 equals the sum of forces in x doesn't tell us anything very interesting. It just tells us 0 equals 0 in this case because there are no horizontal forces. Now the trick here is what is a good choice of rotation axis? And what is a good choice of rotation axis depends on what forces you're trying to solve for. But in this case, an excellent choice of rotation axis is the center of mass of the beam itself. So we'll say 0 is the sum counterclockwise, and sometimes it helps to say about the COM. Sometimes you can indicate your rotation axis. You might have a point labeled P of the torques. And now The convention here is anti-clockwise minus clockwise, and we're using the center of mass of the beam as our pivot. The gravity force has a line of action which points directly through the pivot, so it contributes a torque of 0 because the lever arm is 0. And this is a useful fact to bear in mind in the future. You often want to choose the pivot so that a force that you don't care about has a line of action that passes through that pivot. So let's do counterclockwise. F2 is a counterclockwise sense about this pivot, and then minus clockwise. So we'll do the torque due to F2 first, and then the torque due to F1. Remember, a torque is perpendicular distance, that's the lever arm, times the force. That's usually the most convenient expression for torque. So since this is a vertical force, we want horizontal distance to be perpendicular to the line of action of the force. So we have the horizontal distance is R2, and then the force is F2. That's anti-clockwise. Now clockwise has a minus sign, so the horizontal distance from the pivot to the line of action of F1 is R1, and then the force is F1. So we really want to measure this horizontal distance to the line of action of this vertical force, and we want to measure this horizontal distance to the line of action of this vertical force, but it's often convenient to make your annotations where they don't get in the way of the diagram. So with some practice, you figure out where to annotate so that your annotations are as legible as possible. This last line immediately tells us that R1 F1 equals R2 F2, or equivalently that F1 over F2 equals R2 over R1. And you might remember on the first day of class we found that the two forces had to add up to the weight of the beam we were supporting, and that the ratio of the two forces was the reciprocal of the ratio of the two distances from the center of mass. And now torque lets us explain that observation from the first day of class. To solve this all the way through, we can take this second equation and solve it for F2 so that we can eliminate F2. So that gives us F2 is R1 over R2 times F1. Then we can take this equation and put mg on the right hand side. We get F1 plus F2 equals mg. Then here's F1. We can substitute our value for F2 over here. Then we want to combine these two terms, so we can multiply the first term by R2 over R2, which is just 1. Now we have a common denominator here, so we can call this R1 plus R2 over R2 times F1 equals mg, which we can then solve for F1. F1 equals R2 over R1 plus R2 times mg, since this R2 moved up here and this R1 plus R2 moved down here. By analogy, we could do the same steps and get F2 equals R1 over R1 plus R2 times mg. Then to go back to one example from the first day of class, if one support, let's say support number 1 is 2 units away from the center, and support number 2 is 1 unit away from the center, then the force held by the first support will be 1 over 3, 1/3 of the total weight, and the force held by the second support will be 2 over 3, is 2/3 of the total weight. One thing you might wonder is, what if you picked a different axis? Well, it turns out that depending on what you're most interested in, sometimes it is really convenient to pick a different axis. For example, suppose we wanted to find a shortcut that would get us directly to this equation without so much algebra. Notice that this result contains F1 and it doesn't contain F2. So we were looking for an expression that eliminates F2. One way to eliminate F2 is to make the pivot go through F2. Let's see what happens if we make the pivot go through F2. So let's pivot about a point through which the line of action for F2 passes. So I've drawn my pivot here, just to the right of the center of mass by a distance R2. Now notice that the weight of the beam, the gravitational force, is a counterclockwise torque, so that's positive. And notice that F1 is clockwise, so that's negative. So we will write perpendicular distance to the gravity force is R2, and then minus R1 plus R2 F1 equals 0. We can then immediately solve this for F1. We get F1 equals R2 over R1 plus R2 mg, which is the same result we got over here, but we had to do much more work to get it over here. Once you get good at this, by choosing the right pivot, you can save yourself some algebra. So you only get 3 equations worth of information for equilibrium in a plane, so you really only have 3 independent equations. So if you choose a different pivot, you won't get any new information. You'll just get something that would have come out of a linear combination of the other 2 equations. But sometimes you can get much more directly to the result you want by clever choice of a pivot. There are also some special cases where you can use 2 pivot equations plus 1 force equation, but just file that fact in the back of your mind. Almost always we will use 1 force equation in X, 1 force equation in Y, and 1 torque equation with carefully chosen pivot. And again, if you feel that you don't know how to make a clever choice of pivot, the only thing that's lost is you have to do a bit more algebra to get the final answer. So the only thing that a clever choice of pivot typically does for you is save you a little bit of math. A beam of mass big M and length big L is attached to a wall by a hinge. A sign of mass little m hangs from the end of the beam. The end of the beam is supported by a cable at a 30-degree angle, theta equals 30 degrees, with respect to the horizontal beam, which is anchored to the wall above the hinge. Oh, what forces act on the beam? Draw an extended free body diagram. Find the cable tension T. Find the reaction forces, Fx and Fy, exerted by the hinge on the beam. What 3 equations can we write for the beam? As the problem suggests, the first step in such problems is often to draw an extended free body diagram. So let's do that now. Let's start by drawing the beam, labeling it as a beam, and indicating where its center of mass is. Now let's figure out what forces act on the beam. Usually our first choice is gravity. The line of action of gravity passes through the center of mass of the beam. Gravitational force by Earth on the beam is big M times little g. This hinge is capable of exerting both horizontal and vertical forces on the beam. So let's draw both of those forces. You can give it a long textbook style name like contact force by the pivot on the beam, y component, contact force by the pivot on the beam, x component, though in this case I would probably give it a shortcut name, either fx and fy, or sometimes you might call it px and py since it is exerted by the pivot at point P. So it'll be pretty common later if forces are happening at some point P to call them px and py, or if they're happening at some point A to call them ax and ay. But for now, let's call this fx and fy. We need two more forces. First is the contact force by the sign, really the cable that holds the sign, on the beam. Let's just call that the contact force by the sign on the beam. So there's F, contact by the sign on the beam, and that's little mg. You know that as long as the sign is not accelerating, that this force will just equal the weight of the sign. Although it is an interesting fact that if this sign were accelerating, that force could be different. But usually in static equilibrium, we're treating everything as static. Then we have the tension. So this is, you could call it the contact force by the cable on the beam, but really it's just the tension T, and it helps to indicate this angle theta, which we're told is 30 degrees. Let's do one more thing at this stage. Let's decompose the tension force into x and y components, which will make our equation writing easier. Okay, we have horizontal forces fx and t cosine theta. We have vertical forces fy, mg, little mg, and t sine theta. Now in this problem, there is a natural choice of pivot at this point P. We could use other pivots, but since we have such a natural pivot, let's do that. The next step is to figure out what three equations we can write for the beam using our extended free body diagram. How do we write the statement that the sum of the horizontal forces acting on the beam equals 0? And remember, our usual sign convention is to say plus, minus, minus. So right minus left. It seems as if acting to the right, we have at least the way we've drawn it, the reaction force, the force exerted by the pivot in the horizontal direction. Since we drew it to the right, we could have drawn it to the left, and then we would just get the same answer with a minus sign. So we have fx minus, and then to the left is t cosine theta. Now, one thing I didn't plan, my convention is to say the sum of the forces in x, just to write it as sum fx. So this use of f sub x is completely different from this use of f sub x, which actually represents this horizontal force up here. I hope that's okay. So I think I like answer C, Charlie over here, f sub x exerted by the pivot on the beam minus t cosine theta equals 0. Next, how do we write that the sum of vertical forces acting on the beam equals 0? And the convention I like to follow is upward minus downward forces. Upward, we have this vertical support force exerted by the pivot. We actually don't know for certain which way it will point, but we guess upward, so we'll stick with the way we drew it. And then we have the vertical component of the cable tension. That's all the up forces. Then we have two down forces. We have the weight of the beam itself, and then we have the contact force by the sign, which basically equals the weight of the sign, assuming that the sign itself is not accelerating. So let's see which of our candidate answers seems to match this. I think I like answer F, foxtrot, pivot force in the y direction plus t sine theta minus big mg minus little mg equals 0. So there we go. I think I like answer F. So we've been recapitulating all along. The beam has mass big M and length big L. The sign has mass little m. The cable is at an angle theta with respect to the horizontal, and the hinge exerts a rightward force F sub x and an upward force F sub y on the beam. And again, if we guessed wrong about the directions of the hinge forces, we would just get a negative answer. So you just want to write the equations corresponding to the way you drew the arrow, and if you get a negative number, then you know you drew the arrow the wrong way. How do we write the sum of the torques about the hinge equals 0? And again, maybe we could have chosen a different pivot, but we chose the hinge as our pivot. So using the hinge as our pivot, and I've drawn this as P. So the sum of torques counterclockwise minus clockwise about the point I've drawn here as P, the letter tau for torques. So let's go through. So there's 0 torque from the hinge force in the horizontal direction because our pivot is the hinge. There's 0 torque from the hinge force in the y direction because the hinge is our pivot. And let's try to do counterclockwise minus clockwise. We'll go through the counterclockwise ones first. So this would be clockwise, this would be clockwise. Now the horizontal component of the tension is also drawn in such a way that, assuming that we neglect the thickness of the beam, then this torque is 0 because this is a horizontal force, so it would need a vertical displacement. So if we knew precisely the thickness of this beam, then we could write a term for this horizontal force times the vertical displacement with respect to our pivot. But since we didn't label any dimension for the thickness of this beam, I think we're treating it as a beam whose thickness is negligible compared to other dimensions in the problem. So I think for our purposes, we can say that the line of action of this horizontal component of the tension just passes right through the pivot. Whether it did or not, I think would depend in detail on how we attach this cable. So I drew it as if we attached the cable to the very tip of the beam. Maybe in fact we attached the cable to a little hole drilled through the center here. In that case, even if we knew the thickness of this beam, the line of action would pass directly through the pivot, since the pivot also passes right through the vertical center of the beam. One way or another, this horizontal component of tension either has a line of action that passes directly through our pivot or has a line of action that passes through our pivot with a vertical displacement that seems to be so small that we're neglecting it. So there's zero contribution from t cosine theta. T sine theta, however, this would be a counterclockwise torque. So we'll say t sine theta, and then this is a vertical force. The appropriate displacement is a horizontal displacement, and that seems to be the entire length of the beam. So the first term we get here is the length of the beam times t sine theta with a plus sign because it's counterclockwise. That's it for counterclockwise contributions. Now for clockwise contributions, we have the weight of the beam itself, and it has a lever arm of half the length of the beam. So there's L over 2 for the lever arm, the horizontal distance from the pivot to the point of application of the force to the line of action of this gravitational force acting on the beam. So this is a vertical force. The gravitational force is a vertical force, so we want the horizontal displacement from the pivot to get the lever arm. So that's L over 2, 1/2 the length of the beam. Then we have the weight of the sine. The weight of the sine has a line of action that passes through the end of the beam. So this is the entire length of the beam. This is a vertical force. We want the horizontal displacement to go with the vertical force, and the appropriate horizontal distance is the entire length of the beam. So that's all the terms we have. Big L t sine theta minus L over 2 mg capital M minus L lowercase mg equals 0. So that seems to be answer F foxtrot. I didn't use my positive minus negative convention when I wrote these answers down. So the positive term is LT sine theta. We have that same positive term here. The negative terms are minus L over 2 mg and minus L little mg. So I think I like answer F foxtrot. Next, let's solve this system of equations so we can get the tension. We have 3 unknowns. By the way, in statics in a plane, you only get 3 equations, so there are only 3 unknowns you can solve for. So you have to make sure you don't have more than 3 unknowns. So our 3 unknowns are this horizontal force exerted by the hinge on the beam, this vertical force exerted by the hinge on the beam, and the tension. Why does the tension count as only one force, whereas the force exerted by the hinge counts as 2 forces? And it's because we don't know how this force exerted by the hinge is divided between horizontal and vertical components. We have no idea what the ratio of horizontal to vertical parts is until we solve the problem. By contrast, we are told what the angle is for the cable. The force exerted by the cable has to point along the axis of the cable. So since we know the direction, there's only one component here that we don't know. Since we don't know this direction, we have 2 unknown components. So that's 1, 2, 3 unknowns. Now, this third equation, the torque equation, which we might also call the moment equation, engineers and architects tend to refer to torques as moments of forces. That's like you take the moments of a distribution, like the mean is the first moment, the variance is the second moment of a distribution. So in mathematical terms, the torque is the first moment of force because you're multiplying each force by its corresponding distance from the pivot. So you can call them moments if you like. If you take an architectural structures course, you will call them moments there. But for now, we're calling them torques. So it seems as if the only unknown in this third equation is the tension. So this lets us solve directly for the tension. Okay, that gives us the tension is big mg over 2 plus little mg, all of that divided by sine theta. By the way, this divided by sine theta is kind of an interesting fact. It often turns out that if you apply a force at a small angle, that force has to become very big. So notice, if the cable were oriented vertically, the tension would be only equal to big mg over 2 plus little mg. If you orient the cable at a very small angle with respect to the horizontal, well, it's only the vertical part of that tension which is doing anything useful to support the weight. So we have sine theta in the denominator. So the smaller the angle of that cable with respect to the horizontal, the more difficult its job is. Now that we have the tension, we can easily figure out the horizontal force exerted by the hinge. So we take this tension times cosine theta. So this is cosine theta divided by sine theta. But you know that sine theta divided by cosine theta just equals tan theta. So in fact, this is just like writing tan theta downstairs. Then finally, let's solve for the vertical force exerted by the hinge on the beam. Keeping F sub y on the left side, moving everything else over to the right, we have the sum of the 2 weights minus t sine theta. So that gives us the vertical force exerted by the hinge on the beam is 1/2 the weight of the beam itself, and it seems not to depend on the sine. That's kind of an interesting result. The reason it doesn't depend on the sine is that the sine is hanging directly below this cable. So it turns out that the weight of the sine is carried entirely by the vertical part of the cable and not by the hinge on the other side. So here again is our solution. The cable tension is half the weight of the beam plus all of the weight of the sine, all of that divided by sine theta. The vertical force exerted by the hinge on the beam is just half the weight of the beam and nothing else, and that's kind of interesting. It's a consequence of the fact that the sine is supported just below the cable. And then the horizontal force exerted by the hinge on the beam is half the weight of the beam plus all of the weight of the sine and then divided by tan theta. So the smaller you make this angle with respect to the horizontal, the bigger the horizontal force is that the hinge has to exert to oppose the horizontal part of the tension in the cable. Okay, next let's build a highly simplified model of an arch. I think this model, as simple as it is, does exhibit some interesting features of an arch. So the way we've designed our arch, this is a wooden plank on the left side. This is an identical wooden plank on the right side. They are held together by a hinge. And then at the bottom, the buttressing force that keeps the sides from spreading out is the tension in this string. In fact, the string is a little piece of chain in real life. And then we have the two sides of the arch rest on little skateboards. The reason we rest them on little skateboards is so that we're exerting only a vertical force here, not a horizontal force. That then allows us to measure the horizontal force that is necessary to buttress the sides of the arch so that the arch doesn't just fall down. You can imagine if this little piece of chain were not present, but we have the arch sitting on these two skateboards, I think you can just kind of envision, it'd be like walking on a sheet of sheer ice. It's a bit like my dog if he doesn't kind of keep his legs close together when he's on a really slippery floor. His paws just tend to spread out a little bit and leave him splayed on the ground. So this arch would tend to flatten out if we didn't have some kind of a horizontal buttressing force keeping the two sides close together. So naturally this thing just sort of wants to flatten out. So the advantage of using a separate piece of chain here is that we can put a force scale in the middle of this piece of chain and we can measure how big the tension is that holds the two sides together, and then we can compare that with our calculation. By the way, when we start drawing more little elements of structures, we will see things that look like roller supports. The whole idea of a roller support is that it can exert a force. In this case, if it's a roller sitting on a horizontal surface, then it exerts a vertical force. It exerts zero horizontal force because you assume it's a frictionless wheel or frictionless roller, like a frictionless roller skate. A pin or a hinge, by contrast, can exert a force in two different directions. So actually, encapsulated in this really simplified model of an arch, we have some things that will repeat many times later in the course. We have the idea of a horizontal buttressing force that you've seen when you studied Gothic cathedrals, for example. We have the idea of a hinge or a pin connection, which can exert a force, but it cannot exert a torque. So it does not resist rotation about this point, but it can exert a force either this way or this way. And then we have the idea of a roller support, quite literally in the form of a roller skate or skateboard in this case, which by design exerts a force only in one direction, but not in the perpendicular direction. And then I think we're also going to see that for a given weight of these side pieces of the arch, if we make this arch tall and thin, we do not need a very big horizontal buttressing force. But if we make the arch sort of short and wide, then we do need quite a large horizontal buttressing force. So that'll be sort of an interesting outcome. And we measure that angle, whether it is short and wide or tall and thin, by this angle theta. So this angle theta between the horizontal and the diagonal, in other words, between the horizontal chain and the diagonal wooden plank, we call theta. So a small value of theta would be a short, wide arch. A large value of theta would be a tall, thin arch. Now, I told you a moment ago that the equations for static equilibrium in a plane can solve for only three unknowns, because you only have three equations: forces horizontally, forces vertically, and torques about some pivot. Yet, we have here in this diagram one unknown tension, two unknown vertical forces, so that's three total, and then two forces that can be exerted by this hinge. So we have five total unknowns, but we only have three equations. So somehow we need to cheat so that we can make this problem solvable using static equilibrium in a plane. The way we're going to cheat is to exploit the symmetry of the situation. So we are actually going to draw a free body diagram, not for the whole arch, but just for one half of the arch, and we will exploit the symmetry. Another trick you'll see us use when we exploit this symmetry is that it is possible for the left and right sides of this arch to be pushing toward each other or away from one another. So a horizontal force by this hinge is certainly possible, not just possible, but really mandatory, because the horizontal force by this hinge will somehow oppose this tension. But we can argue by symmetry that there's no vertical force exerted by one side of this arch on the other. For example, imagine that the right side is pushing down on the left side. Well, then by symmetry, you would think that the left side should be pushing down on the right side. Or suppose the right side is pushing up on the left side. Well, by symmetry, then you should think that the left side is pushing up on the right side. So I claim that by symmetry, there is no reason that one side of this arch should be pushing up or down on the other, because if you do a mirror image, you see if this is pushing up on this, and then this is pushing down on the other part, if you then reflected that in a mirror, you would change the sign. So I claim that the mirror symmetry of the situation argues that there must be zero vertical force exerted by the hinge. There can be a horizontal force, because suppose the left side is pushing against the right side. Well, then the right side is pushing against the left side, and when you make a mirror image, that doesn't change. That's fine. But if you had the left side pushing up on the right side, when you make a mirror image, that would flip the sign. So the only way that you can have the mirror image be the same as the original is if the vertical force is zero. That's a little bit of a sleight of hand, but it's a valid sleight of hand as long as we really do build this perfectly symmetrically, and it's a sleight of hand that allows us to solve the problem. So we will do what we need to do to solve the problem. So often the essence of physics is to reduce a complicated problem to a similar but simplified problem that is easier to analyze. So that's what we're doing in this model of an arch. So one piece of information we need to record here before we move on is that the weight of each plank, in other words, the weight of each side of the arch, is 20 newtons. So each wooden plank that constitutes one side of the arch has a mass of about 2 kilograms. So again, we're using a cable or a little piece of chain to hold the bottom together, because that allows us to put a force scale, a little Newton scale, in the middle so that we can measure the tension and explicitly immediately check it against our model. And again, we're going to exploit mirror symmetry and analyze just one side of the arch. So if we draw an extended free body diagram for the right-hand plank, what forces act and where do they act? So let's figure out the forces. Let's figure out the points of application of those forces, and let's figure out the line of action of each force that acts on the right-hand side of the arch. And we will do that as part of drawing an extended free body diagram for the right-hand plank. So here is the right-hand board, or plank. I guess I'll call it B for board. We could have called it P for plank. Let's call it B for board. And then we can call this H for hinge. So the first force is the gravitational force by Earth on the board, which just equals mg. The next force is the tension force, the contact force exerted by the cable. So I'm going to say this is the tension T, which is the contact force exerted by the chain or the cable on the board, and it's horizontal. The next force is the vertical contact force. We could call it the normal force, since we're sort of accustomed to the vertical force exerted by the floor on something being the normal force. So let's call this the normal force exerted by the floor. I mean, it's the roller skate, but let's call it the floor on the board, and we don't know how big that is, so maybe we'll just call this F normal for short. And finally, we have the contact force exerted by the hinge on the board, and we said that there can be a non-zero x component. We argued that it doesn't make sense by mirror symmetry for there to be a non-zero y component, and that's a good thing because that would be then 4 unknowns. We only have 3 equations. So let's just call this the force in x exerted by the hinge. Then in order to draw torques, we will need to figure out dimensions. So let's call the length of this board L. We can compare with the extended free body diagram I already drew on slide 34. I think it has the same features. Tension acting to the left at the bottom corner of the board, normal force acting upward at that same bottom corner of the board, the horizontal force exerted by the hinge, also known as the pin, at the upper corner of the board, and then gravity acting directly downward at the center of mass, also known as center of gravity of the board, and then the length L of the board. How many unknown variables is it possible to determine using the equations for static equilibrium in a plane? Well, we have one equation for force horizontally, one equation for force vertically, and one equation for torque. So that's 3. We have 3 equations. Using those 3 equations, we can determine 3 unknowns. So static equilibrium lets us write down 3 equations for a given object. And in this case, I wrote the third equation as the sum of the moments about the z-axis equals 0. Normally, I would just say the sum of the torques equals 0, and I would indicate the direction of rotation. And I might indicate the point that we're using as the pivot. I'm trying to be a little more engineer or architect-like in writing this down this time. So let's start with the torques, also known as the moments. And let's evaluate our moments about the hinge, which I'll call H, the top corner of the board. To add up the torques about this hinge, let's do counterclockwise minus clockwise. So any force that is applied up here at the hinge has a line of action that passes right through the rotation axis and therefore has 0 lever arm. So we don't have any contribution from this force exerted by the hinge. How about the tension? So the tension would tend to be clockwise. The normal force would tend to be counterclockwise. And then about this pivot, gravity would tend to be clockwise. So let's do normal force minus the other 2. What is the lever arm for the normal force? Well, the normal force is a vertical force, so we want the horizontal distance from the pivot, since it's a vertical force. The horizontal distance from the pivot to the point of application of the normal force, which could also be said as the horizontal distance from the pivot to the line of action of the normal force, is L cosine theta. So we have L cosine theta times the normal force. And we could draw the triangle just to argue that. So adjacent over hypotenuse is this lever arm that we want divided by L, that's cosine theta. So the lever arm that we want is L times cosine theta. So first term, L cosine theta times normal force. Then let's do the tension. What is the lever arm for the tension? Well, the tension is a horizontal force, so we want the vertical displacement for the lever arm. So that must be L sine theta. And we can see that. So in this case, we have R perp. So the orange R perp over L is opposite over hypotenuse is sine theta. So in the orange case, R perpendicular is L sine theta, opposite over hypotenuse. Then we have the gravity force. So this is a vertical force, so we want the horizontal displacement. So this horizontal displacement is just 1/2 of this horizontal displacement. So the normal force was a vertical force whose line of action was L cosine theta away, and the gravity force, the weight of the plank itself, is a vertical force whose line of action is a horizontal distance 1/2 L cosine theta away. So here's our torque equation. 0 equals L cosine theta F normal minus L sine theta tension minus L over 2 cosine theta mg. So I think that turns out to be answer A, alpha over here, minus mg L over 2 cosine theta plus F normal L cosine theta minus LT sine theta equals 0. Next, let's try the sum of the horizontal forces acting on the beam. So I do right minus left usually by convention. To the right we have the horizontal force exerted by the hinge, and to the left we have the tension. So that's pretty easy. We just get that the tension is the same as the horizontal force exerted by the hinge. hinge. Same magnitude, opposite direction. Next, let's try the vertical forces. So I usually do up minus down. In the up direction, we have the normal force. In the down direction, we have just the weight, and that's it. That tells us that the normal force just equals the weight. So let's use these last two equations to eliminate the normal force and eliminate the force exerted by the hinge. So we'll just be left in terms of the tension and the weight. Now we can solve for the tension. So we'll move this term over to the left side. These two terms can stay on the right side. Then we can cancel an L everywhere, and we can combine these two terms since one is just half the other with a minus sign. Then we can divide both sides by sine theta, and the result we get is the tension is mg over 2 tan theta, where m is the mass of one of these boards. So the smaller we make theta, which means that the arch is more short and wide, the bigger the tension we need to hold it together. If we make the arch tall and thin with the same mass, then we need a smaller horizontal force to hold it together. And then you can also see that the tension exerted by the cable in the middle just opposes the kind of compressive force. So a real arch, well, a real dome has a kind of compression ring at the top center. Now let's see how this calculated result compares with our model that we built. So mg is 20 newtons, so we should have a tension of 10 newtons divided by tan theta. So plugging in a weight of 20 newtons for one board, we get that the tension in the cable that holds the arch together horizontally should be 10 newtons divided by tan theta, where this theta is measured with respect to the horizontal. So let's go see how that worked out. Welcome to my basement pool table. Normally my dad beats me on the weekends, but I had a lucky break last weekend. This is our homemade arch. Here's a little skateboard. Here's a little skateboard. The idea then is that the floor can exert a vertical force, but not a significant horizontal force on each board of the arch. Here's one board, here's the other board, and we have a couple of wire ties used as hinges. So this basically forms a pin support between the two boards of the arch. This string with the Newton scale in the middle provides the buttressing force that holds the two sides together. Without the buttressing force, the arch would just flatten out on the table. And then the whole point is we want to see how big this buttressing force is as a function of this angle from the horizontal up to this board. So the weight of the two boards together is 40 newtons. So the weight of one board is 20 newtons, and we worked out then that the force we expect to be read by the Newton scale here is 10 newtons divided by the tangent of theta. The first value we're using for theta is 45 degrees. The tangent of 45 degrees is 1, so we expect 10 newtons. Amazingly, we read 10 newtons here on the scale. To show you this is 45 degrees, well, I'll show you how I know it's 45 degrees. Each one of these two boards is 48 inches long. We're using these old-fashioned units called inches. And this length, in other words, half the width of the base of the arch, divided by 48 inches should equal cosine theta. So that's equivalent to saying that half of the total base of the arch divided by 48 inches should equal the cosine, and I've checked that the total base of the arch from one end to the other is about 68 inches, and my calculation says for 45 degrees it should be 67.9 inches. So I'd say this is pretty close to 45 degrees. By the way, the results agree with my pre-calculated results from slide 43. You could also ask yourself, how would the result change if we suspended a mass from this point at the hinge? So if we suspended some mass big mg from the hinge, so since we use little m for this, let's use big M for this, how would that change the final result? I guess if you were going to do that, you would suspend from a cable here some mass big M, so then you would have big mg applied here, and then by symmetry we're analyzing only half of the arch, so I guess you would put half of the weight here since the other half belongs to the mirror image, so that would be big mg over 2, because the point of application of this force is right at the hinge, or better yet, because the line of action of this force passes through the hinge, which was our pivot. It would not change the torque equation, and it would not change the horizontal force equation, but it would change the vertical force equation. So instead of little mg, we would have little mg plus big mg over 2 to balance the normal force, and then I guess we could just fill in the rest of the results. So I don't think I want to go ahead and do that here. I think I might leave it as a homework problem, or if you're feeling really ambitious, maybe it could be an extra credit problem, but I think I might turn it into a homework problem to ask what would happen if we suspended an extra mass big M from the hinge here. How would that affect the tension? I think if you worked it out, you would get that the new value for the tension is big M plus little m times g over 2 tan theta, but you're gonna have to check me on it. Yeah, so I think that's what the new answer would probably be, but you should check to be sure. This is about the widest I can make this arch and still fit on the ping pong cover of my basement pool table. The full span of the base of the arch is about 84 inches, and then the length of one board here is 48 inches. Half of this full width, so the half width, divided by the hypotenuse, which is the length of one board, is the cosine of this angle with respect to the horizontal. So putting in the numbers, I get that the angle right now between the horizontal and this diagonal is about 29 degrees, and the force that I expect is 10 newtons divided by the tangent of this angle. We worked that out because the two pieces together weigh 40 newtons, so one piece weighs 20 newtons, and we worked out 10 newtons divided by tan theta for the expected string tension, the expected necessary buttressing force. I expect 18.1 newtons, I see right about 18 newtons. That's probably a little better than I deserve. Let me add 400 grams at the center. So that should be, that's 0.4 kilograms. That's 4 newtons. So then I expect 2 newtons divided by tan theta. 2 newtons divided by the tangent of 29 degrees should be about 3.6 newtons. So I think I expect this number to go up by about 3.6 newtons. So I think that should bring it up to just below 22. It does seem to go up to just below 22. That's not bad. Now I set the full width of the base to be about 68 inches, and according to my calculation, this should be pretty close to 45 degrees. Yeah, so a 68-inch full width of the base should give me very close to a 45-degree angle here. So then I expect 10 newtons divided by the tangent of 45 degrees. The tangent of 45 degrees is 1, so I expect the scale to read 10 newtons. The scale, in fact, reads, about 9 newtons. 9.5 newtons. So that's not too bad. Then, if I add 10 newtons of force to this point at the apex, I expect the reading to increase by 5 newtons. Let's see how that works. But it should be 10 newtons divided by 2 divided by tan theta. So that should be 5 newtons divided by tangent of 45 degrees is just 5 newtons. So it's a 5 newton increase from what we see here. Depending on how exactly I wiggle it, I'd probably see somewhere between a 4 and 6 newton increase. So that seems pretty good. Just for fun, I can add an additional 10 newtons. So now it should be pretty close to 20 newtons total that I read on the scale. Yeah, depending on how I jiggle things, there's a little bit of friction, so every time I jiggle it, I think the friction does something a little bit different. So I get somewhere between 19 and 21 newtons total, depending on the luck of sort of wiggling and releasing things. So I see here I got 19, here I got 21, here I got 20 and a half. Okay, that's 20. So that seems pretty compatible with our model. Okay, now I've reoriented so that the full span, the full width of the base is about 50 inches. So that gives me, this angle theta is about 58 or 59 degrees, a little closer to 59. So for 59 degrees, I expect a force of 6.1 newtons. I see about 5.6 newtons. Now I see about 5.0. Now I see about 5.5. Now let me add an additional 2 kilograms of mass here, so that should be 20 more newtons down. So adding 2 kilograms, that's adding 20 newtons up here, should increase the scale reading by 20 newtons divided by 2 tan theta. That's another 10 newtons divided by tan, 59 degrees. So it should double our reading from about 6 newtons to about 12 newtons total. Let's see how that works. That's not bad, you see? So we see about 12 newtons total versus about 6 newtons total originally. So I'd say our model works pretty well.